Right. I don't know if it's working or not, but okay. Hello everyone. Today we'll be talking about blood gas transport. I've honestly not had that much time to create a PowerPoint, so we're just gonna go over the slides for the doctor, and inshallah we're not gonna take that much time. So I hope CVP studying is going well for you guys. And inshallah this makes blood gas transport really easy. Most of it was covered in Dr. Hanat's lecture and more, so inshallah all will be fine. Okay, so first of all, physically dissolved oxygen. Gas transport by the blood. We have in the blood we have oxygen dissolved and oxygen binded to hemoglobin. Dissolved oxygen, you guys need to know that basically for each millimeter of mercury of partial pressure of oxygen, there is 0.003 milliliters of oxygen per 100 milliliters of blood. Thus, normal arterial blood with a partial pressure of oxygen of 100 millimeters of mercury contains 3 milliliters of oxygen in a liter of blood. Normally, our cardiac output is 5 liters per minute, so we'd normally have like 15 milliliters per minute. Okay? Only in dissolved form can oxygen diffuse through alveoli capillary membranes and blood plasma in the lung or through cell membranes and cytoplasm of the cells in tissues. So it's only when oxygen is dissolved that it can diffuse through all the membranes. Okay. This is the oxygen binding curve of the blood. So this basically shows that the concentration of oxygen combined with hemoglobin is basically the difference between the total and dissolved oxygen concentrations. So you inhale oxygen, right? That becomes basically the alveolar pressure of oxygen, whatever inspired oxygen. And muhim innu, basically the main point is that the chemically bound hemoglobin oxygen, it can be calculated by subtracting the total oxygen from the dissolved oxygen, okay? Because we're going to have the dissolved oxygen and the chemically bound oxygen in our blood, okay? And then we need to know that note that the amount of oxygen carried by the hemoglobin increases rapidly up to a pressure of about 50 milliliters of mercury, but above that the curve becomes much flatter, and this we're going to talk about it more. This is basically the half point, you could say, the point where basically the hemoglobin is 50% filled with oxygen, okay? The maximum amount, and basically after that 50%, the curve becomes more flatter, which basically means that even though basically you could have less oxygen in the air, less oxygen inhaled, whatever, that's not going to change that much because it's already binded to hemoglobin. And we're going to talk about that in a bit. So here you need to also know that the maximum amount of oxygen that can be combined with hemoglobin is called the oxygen capacity. On 1 gram of pure hemoglobin can combine with 1.34, so normal blood has about like 15 grams. And try to memorize this number, it's quite important. The oxygen capacity is about 20.1 milliliters of oxygen per 100 milliliters of blood, okay? This is capacity. So this is the maximum amount of oxygen bound with hemoglobin, right? No, that is 20.1 milliliters, okay? So let's move on. Equilibrium between physically dissolved and chemically bound gas. This one is pretty easy. So basically you have oxygen physically dissolved. This, like, let's say you've got 2 containers. One of them has a lot of oxygen, the other. So basically you put all the oxygen in container A. What's going to happen is that the molecules are going to go to container B until the partial pressures are equal. And here you can also see that the partial pressures are equal, even the concentrations are equal. However, in the one here in the middle, when you add hemoglobin, what's going to happen? When you add hemoglobin, there's going to be oxygen binding to the hemoglobin, so you're going to have a lower partial pressure of oxygen in container B. So there's going to still be more oxygen particles moving from container A to container B to reach equilibrium. Like as you see in the last two containers, you have A, it only has 2 particles of oxygen, B only has 3 particles of oxygen, while all the rest are bound to hemoglobin. And this basically shows what happens. This basically shows that the concentration, sorry, I'm trying to get to concentration. The concentration in the last container in B would be more than A. All right. So the higher the dissolved oxygen concentration, and thus the partial pressure of oxygen, the greater would be the oxygen concentration combined with hemoglobin. This basically means that the more oxygen you have in A, the more bound oxygen particles you're going to have with hemoglobin. So the driving force is always going to be the partial pressure difference. Equilibrium is then achieved only by the equality of oxygen partial pressures, we've already said that, and not by equality of concentrations. So as you can see here, these don't have equal concentrations, but they have equal partial pressures, and that's it. Here we have the oxygen binding curve of hemoglobin. Oxygen saturation of hemoglobin is defined as the percentage of the available hemoglobin binding sites that have oxygen attached. This is basically what is oxygen saturation of hemoglobin? The percentage of the available hemoglobin binding sites that have oxygen attached. Okay. It's important to note that this curve does not include the physically dissolved oxygen. This is only for basically the oxygen bound to hemoglobin. As seen in the figure, the oxygen saturation of arterial blood with a partial pressure of 100 millimeters of mercury is about 98%. However, in mixed venous blood with lower partial pressure of oxygen, which is basically 40, you're going to have about 75%. 75% saturation. And this, I want to, basically, this is what we said here. The higher the dissolved oxygen concentration, and thus the PO2, basically, the greater would be the oxygen concentration combined with hemoglobin. So the higher the pressure you have, the higher the oxygen concentration you're going to have bound with hemoglobin. Same thing we can see here, about 98% is saturated when there's a higher partial pressure, basically 100. When you have 40 partial pressure, you're going to have only 75% saturated. Okay, so the oxygen saturation is 50% at normally a partial pressure of 27. This is basically the P50, okay? And it is used to measure the affinity of hemoglobin. So the lower the partial pressure, like let's say you get your P50 at a partial pressure of oxygen less than 27. That basically means you have higher affinity, and we're going to come to that in a second. The curved shape of the oxygen saturation curve has several physiological advantages. The flat upper portion means that even if the partial pressure of oxygen in alveolar gas falls slightly, alright, the loading of the blood with oxygen will only be mildly affected. And this is what I was trying to say earlier. So like even if you're climbing to high altitudes, and you've got lower partial pressure of oxygen, this flat upper portion, what it does, it shows that you still have oxygen bound to hemoglobin, right? And that basically means that that oxygen isn't lost, so it can still be dissolved into the tissues. Okay, so it's only going to be loading of the blood with oxygen will only be mildly affected. The steep lower part of the dissociation curve means that the peripheral tissues can withdraw large amounts of oxygen for only a small drop in capillary partial pressure of oxygen. So even if you have a small drop, like here, as you see, there's not a big difference in partial pressure, but already you lose most of the oxygen that was in the hemoglobin, or like the tissues take most of it. All right. One more thing is that the driving force for oxygen diffusion is partial pressure of oxygen, difference between capillary and tissues. Here we have basically the oxygen binding curve of hemoglobin, the saturation, we've talked about it, and this is the oxygen binding curve of the blood, we've talked about both of them. Just know that a decrease in partial pressure of oxygen would cause a reduction in both oxygen saturation and oxygen concentration. So if you have a decrease in partial pressure of oxygen, you're going to have less oxygen saturation, which we previously explained, and even less oxygen concentration. And we've also talked about that before. So let's say, so like here, for example, you have less partial pressure of A, you've got less particles of A, so you've got less partial pressure. So you're going to have a less concentration, obviously, right? However, a decrease in hemoglobin concentration, and I want you to focus on this, would only cause a reduction in oxygen concentration, but not in oxygen saturation. Remember, what was oxygen saturation? Oxygen saturation is defined as the percentage of the available hemoglobin binding sites that have oxygen attached. So that basically means that it basically gives us the affinity, right? So it gives us the affinity of oxygen with hemoglobin, or hemoglobin to oxygen. So that is not going to be affected if the oxygen partial pressure is decreased. It's still going to have the same affinity. Okay? And that's why we also said here that the flatter proportion means that even if the partial pressure of oxygen in alveolar gas falls slightly, loading of the blood with oxygen will only be mildly affected because the saturation isn't affected that much. Okay? Now, let's move on. I hope that made sense. If it did, if it didn't, like, you can always like go back and rewind and listen to that again. Influences on oxygen binding curve of the blood. Okay, we've already talked about this. The affinity of hemoglobin for oxygen is represented by the P50. P50 is defined as the partial pressure of oxygen required to achieve 50% hemoglobin saturation. Normally, it's 27. Basically, this is at 37 degrees Celsius and normal pH. The P50 is less. If it's less than 27, then it has a higher affinity, and that is the green curve we can see. And if it's a right shift, which basically indicates a lower affinity for oxygen, which means a higher P50. So higher P50, lower oxygen affinity, lower P50, higher oxygen affinity. Which it basically means less pressure required to reach the 50% hemoglobin saturation. It basically makes sense if you like say it to yourself over and over again. Anyways, so what influenced these P50? We've got hydrogen ions, carbon dioxide. We've talked about this before. What do hydrogen ions do? When you have more hydrogen ions, you're going to have a shift to the right, which basically means lower affinity. You're going to have oxygen leaving hemoglobin. Why? Because hydrogen binds reversibly to the imidazole group of the amino acid histidine. We're going to see this in a second. There's like a structure. What hydrogen does, it binds to hemoglobin, oxygen leaves. Okay, cool. Basically means more hydrogen ions, more oxygen leaving hemoglobin, and this is good only when we're trying to release oxygen into the tissues. Okay, so this is good when we're at the tissues, and this is basically called the Bohr effect. Okay, carbon dioxide, what it does, also same thing, more carbon dioxide, less affinity, right shift. How? Two ways. More carbon dioxide means more H plus. Also, carbon dioxide binds to the N terminus of the alpha and beta chains of hemoglobin, also reducing the hemoglobin affinity for oxygen. Cool, cool. Let's go next. This is what I was talking about. Hydrogen binds to hemoglobin, oxygen is released. So this makes a right shift. Okay, and this equation we're going to talk about in a bit. Temperature also, when you have higher temperature, you're going to have a right shift. As you can see here, 41 degrees causes the right shift, 33 degrees causes the left shift. Just know that when, I don't know, exercising, a lot of heat, you're gonna release more oxygen. 2,3 diphosphoroglycerate also, or BPG, bisphosphoroglycerate. By the way, bi, same thing. They both mean two in Greek, Latin, whatever. So when you have more 2,3 DPG, what happens is the curve shifts to the right. This happens when you have, it basically helps you to release oxygen, and this basically happens when you have chronic hypoxia, or you're at like a high altitude, or in the presence of chronic lung disease. So this is basically what your body does to help you release the oxygen. Okay, cool. In the tissues, of course. Influences on blood oxygen binding curve. This is basically a summary of all what we just said. Okay, so this part is important. Carboxyhemoglobin. Hemoglobin loaded with oxygen, 100% saturation. This is normal, okay? Now, when you have 50% anemia, what does that mean? That means we have less hemoglobin. When we have less hemoglobin, would that affect the saturation? No, that would not affect the saturation. Remember, saturation is like affinity. Oxygen's affinity to hemoglobin will not be changed, okay? If hemoglobin is decreased, it will be changed with these factors, okay? The affinity would be changed with the hydrogen ions, carbon dioxide, temperature, 2,3-phosphoglycerate, and the type of hemoglobin, which we also took, which you can read the slides. We took it before. Anyways, so this guy has anemia. His hemoglobin is still going to have normal affinity. However, he's going to have less oxygen in his blood, of course. 50% saturation of hemoglobin with oxygen and 50% with carbon monoxide. Remember, this is carbon monoxide. Carbon monoxide poisoning, we're going to talk about right now. Okay, so what does it do, carbon monoxide poisoning? Carbon monoxide has about 240 times the affinity of oxygen for hemoglobin. This basically means that carbon monoxide will combine with the same amount of hemoglobin as oxygen when the carbon monoxide partial pressure is 240 times lower. What does that mean? That means that basically you just need a very small amount of carbon monoxide for it to straight bind to hemoglobin, and that's not good. When it binds to hemoglobin, what it does is basically it shifts the curve to the left. However, it decreases the amount of oxygen bound. Okay, so this basically says if alveolar gas contains only 0.1% carbon monoxide, then 50% of hemoglobin binding sites will be loaded with carbon monoxide. Okay, what I'm trying to say is that 50% of its when we have carbon monoxide, 50% of its hemoglobin is loaded with carbon monoxide. This is the green curve. What happens? The presence, right, or the 50% carbon monoxide loading shifts it to the left, right? The presence of carbon monoxide shifts the oxygen association curve to the left, interfering with the unloading of oxygen. Now, it shifts it to the left. When it shifts it to the left, that means more affinity for oxygen, right? Now, how does that happen? This is part of the toxicity of carbon monoxide. It changes the structure of hemoglobin, and that makes carbon monoxide, it makes oxygen less releasable, or like less, it gives it a higher affinity to hemoglobin, all right? And now this is a problem. Cigarette smokers, they have about 50% of their hemoglobin bound with carbon monoxide, and this is going to give you the poisoning. So what's going to happen? The oxygen concentration is going to be grossly reduced. The blood partial pressure of oxygen is going to be normal. The alveolar carbon monoxide fraction is still going to be low, so you're still going to have normal partial pressure of oxygen in the alveoli. However, in the blood, it's going to be reduced, alright? Severe carbon monoxide poisoning may require blood transfusions or treatment of the patient with hyperbaric oxygen. So, how do we fix this situation? We need to remove the carbon monoxide from the hemoglobin, because what it's doing is that not only it's reducing the oxygen in the blood, however, it's making the oxygen that's bound unable to be released. So we need to fix this. How do we fix this? There's a treatment of the patient with hyperbaric oxygen, which basically means giving him oxygen at very high partial pressures, and that very high partial pressure would push the carbon monoxide away and make the oxygen bind. And there's also blood transfusions. Okay, let's move on. Oxygenation and oxidation. Just know from this slide that if we have heme is basically, iron, right? Iron in Fe2 plus. So if it's oxidized and it's converted into Fe3 plus, the Fe3 plus cannot bind to oxygen, and that is called methemoglobin. How do we convert it from methemoglobin back to normal hemoglobin? There's an enzyme called plasma methemoglobin reductase. People who have deficiency plasma methemoglobin reductase are gonna have a reduction in their oxygen carriage capacity, because they're not gonna be able to carry oxygen in their hemoglobin, because their hemoglobin is changed, of course. All right, so Oxygenation is normal. You give it oxygen, you release oxygen. That's just basically the normal form when it's 2 plus. Okay. However, oxidation is when it Fe2 plus converts into Fe3 plus methemoglobin can't bind to oxygen. Cool. Tamam. Now we've got three forms of carbon dioxide in the blood. It can be physically dissolved. Remember, it can be also bicarbonate, and it can be bound with proteins such as carbamino compounds. Okay, so dissolved carbon dioxide has about 20 times more solubility than oxygen. So when it's dissolved, that makes about like 10% of its transported form. I think that makes sense. Anyways, when it's bicarbonate, how is it bicarbonate? So when carbon dioxide wants to enter the blood from the tissue, bicarbonate is formed. How does that happen? Remember, blood from the tissue. So in the tissues, we've done our ATP reaction, whatever, and Muhim, we have carbon dioxide. We want to release that carbon dioxide. What we do, the carbon dioxide moves from the from the tissues to the blood, and in the blood, it is converted to bicarbonate. Now, how does that happen? Carbon dioxide with water. Where does this happen exactly? It happens in the red blood cells. So this reaction is very slow in plasma. However, it is very fast within the red blood cells because of the presence of the enzyme carbonic anhydrase, which is in the red blood cells. So in the red blood cells, what happens when the concentration of these ions increase? H plus is buffered by hemoglobin, and HCO3 minus is transported into plasma by carrier exchanging chloride. This is important. So when this reaction happens in the red blood cells, what happens exactly? H plus is made, and HCO3 minus is made as well, but it's transported into the plasma by a carrier exchange. So what happens? We do this reaction in red blood cells. We make H plus. We make HCO3 minus. This HCO3 minus is gonna go it's gonna go out to the plasma in exchange for chloride. The chloride is gonna go back into the red blood cell. Now, this reaction is reversed. Where is it reversed? It's reversed in the lungs when you want to release the carbon dioxide. So you're going to have more HCO3 minus and more H plus to convert it back to, convert it back to carbon dioxide. Okay, just know that the most transported form of carbon dioxide is the bicarbonate. Cool. Carbamino compounds. This is basically the combination of carbon dioxide with terminal amino groups in blood proteins. The most important protein is the globin of hemoglobin. Deoxygenated hemoglobin can bind more carbon dioxide as carbaminohemoglobin than oxygenated hemoglobin. Thus, unloading of oxygen in peripheral capillaries facilitates loading of carbon dioxide, whereas oxygenation in the lung has the opposite effect. And this is called the Haldane effect. We're going to come to it in a second as well. It basically means that when you have more oxygen in the lungs, so you're going to have more hemoglobin binding to oxygen, what's going to happen? We're going to have unloading of carbon dioxide, less carbon dioxide bound. And when you have deoxygenated hemoglobin, when when you want to take the blood out of your body, or take it out like in the tissues, you've got deoxygenated hemoglobin, more carbon dioxide can bind. Okay. So this is the carbon dioxide dissociation curve. Just know that there is no maximal value for chemically bound carbon dioxide, and it increases along with the increasing partial pressure of carbon dioxide. This is what I was going to talk about. We have this reaction where? In the lungs, when we want to release the carbon dioxide. So addition of H plus to the blood causes the release of carbon dioxide from binding site, and this is the carbon dioxide exhaled in the lung. Therefore, the total concentration of carbon dioxide decreases, and the carbon dioxide binding curve shifts to the right. Also, increased temperature releases carbon dioxide from binding sites and shifts the curve to the right. So just like oxygen, we have more temperature, it's going to release it more. Even in oxygen, when we have more temperature, we're going to release it more as well. And yeah, this is what I wanted to talk about, the Haldane effect. What is the Haldane effect? It's basically the effect of oxygen on carbon dioxide and H plus in combination with proteins. So basically, remember when we have the Bohr effect, when we had more H plus, more carbon dioxide, they're going to bind to hemoglobin, oxygen is going to be released. Now we have less H plus, less CO2, so we're gonna have more oxygen, and oxygen is gonna bind to hemoglobin, and H plus and CO2 are gonna be released, and that's pretty much it. This effect facilitates carbon dioxide loading in the tissue capillaries and carbon dioxide unloading in the lung. Therefore, oxygen causes a right shift in carbon dioxide binding curve. Boron Haldane effects, we've already talked about them, and this is basically what happens in the mother blood and the fetus blood when you're a baby. You basically have a double Bohr or Haldane effect. Basically, you have your as in the fetus blood, you're receiving oxygen, reduces the affinity for carbon dioxide, and the leaving carbon dioxide increases the affinity for oxygen. I mean, you can take a look at this by yourself. I think it'll make absolute sense for you. All right. Thank you for this lecture. I hope it made sense, and good luck with your studies. The CPV final. CPV final is just around the corner. Right. Anyways, thank you guys. See you. Sorry it was a bit long.